Hi, I'm Kinman Lee.
Hi, I'm Arjun Krishna.
We will be presenting our paper titled The Effect of Robot Skill Level and Communication in Rapid Proximate Human Robot Collaboration. Our co authors are Zulfikar Zaidi, Rohan Palija, Litin Chen, Aaron Headland Body, Mariah Strum, and Matthew Gombolay. This work was funded by a gift award from Google. As high speed agile robots become more common, these robots have the potential to better aid and collaborate with humans. However, this increased agility can alter team dynamics in collaborative settings and degrade task performance. Creating effective robots for human robot teaming thus requires understanding how the robot's design and characteristics impact the overall team dynamics. Most of the literature on human robot collaboration report findings based on studies that are conducted on slow moving robots or virtual environments. To fill this gap, we developed a system that enables safe and dynamic human robot collaboration and conduct a full user study in this environment. Our work is grounded in a modified table tennis environment that's shown on the videos here on the right. Prior work have investigated the impact of robot skill, communication, and voice design on collaboration dynamics such as perceived trust and safety, and their influence on overall team efficiency. We wanted to extend this to an environment that required fast paced collaboration. In particular, we wanted to understand how the robot's skill level, communication, and sex of the robot's voice affect perceived trust, perceived safety, and overall team performance. By studying these factors in an agile, proximate environment, our work can help inform improved designs to create efficient, collaborative robots in the real world.
In our study environment, we use a regulation ping pong table with a ball feeder to launch balls to three different zones. The robot is designed to swing at the balls in Zone R, the robot zone, and the Zone S, the shared zone. The participant is free to hit any ball they want, but are solely responsible for the balls that land in Zone H. The participants are constrained to start from the home position prior to every ball launch. We remove the doubles requirement to switch players after every hit, so the participant must actively decide if they want to attempt the ball. The objective of the participant is to work with the robot to maximize the team score by returning as many balls as possible in a round. Each round consists of a randomized sequence of 30 balls, and the participant can keep track of the score on a display as the round progresses.
Our system has five main components to enable the robot to successfully return the balls and keep the participants safe throughout the user study. The first is the pose estimator, which utilizes camera-based human pose tracking to output 3D key points of the human joints. The workspace intrusion detector uses the key points to determine if the participant has crossed the robot workspace. For ball tracking, we utilize a multi-camera vision system to detect and track the ball. The ball strike controller utilizes probabilistic movement primitives trained to return the balls. Finally, the safe executor executes the striking motion and stops the arm in place if a workspace intrusion is detected. For the study design, the factors in our user study are the sex of the robot's voice, the robot's skill at returning the ball, and robot communication. The sex of the robot's voice can be male or female, and we designed it as a between subjects factor to prevent participants from realizing we are investigating sex or gender bias. Robot skill and communication are within subject factors. The robot skill can be high or low. When in the high skill condition, we use the best performing model of the ball strike controller. When in the low skill condition, we slightly mistime the robot swing 50% of the time so that the robot fails to return the ball. For robot communication, it can be enabled or disabled. When enabled, the communication is a bi-directional channel where the robot can verbally speak to the participant and vice versa. The robot will assert its intent quickly by saying, "mine," or "got it," prior to swinging at the ball. The participant can also choose to do the same, and the robot responds by stopping immediately. Due to latency constraints of voice recognition, we stop the robot through a Wizard of Oz paradigm by pressing a button after the participant speaks.
We report our analysis with 42 participants recruited from around the Georgia Tech campus. The key metrics we examine in the study are perceived trust, perceived safety, team performance, which is the total number of balls successfully returned in a round, and the human initiative in the shared zone, which is measured by the number of balls landing in the shared region yielded to the robot. Here are some of the key results. We observe that the participants trust the robot less when it performs poorly, confirming with the findings from earlier studies situated in non agile settings. Additionally, we find that communication did not impact the level of trust in the robot. We find that communication significantly lowered the robot's perceived safety, with the male voice perceived to be less safe. We hypothesize that the constant announcement of the robot's intent induces more anxiety and agitation in such a fast paced setting. For the team performance metric, as expected, we observe that teaming with a better performing robot resulted in higher scores. But surprisingly, communication degraded the team performance, especially when the robot performed poorly. We measure human initiative in the shared zone by the percentage of balls landing in the shared region yielded to the robot to attempt, indicating the reliance on the robot. With no communication, robot with a higher skill was given more chances to attempt the shared task. From the data, we observe that having higher skill and enabling communication increase the odds of the robot getting to perform the shared task.
Here are the key takeaways from our paper. We introduce a table tennis environment to study rapid and proximate human-robot collaboration. We find that a robot that assertively communicates its intent is detrimental to the team performance in such a setting, especially when the robot performed poorly. This form of communication also lowered the robot's perceived safety, potentially due to the sensory overload of the user, as the participants in our study had to track the ball, factor in the robot's intent, and decide if they wanted to attempt the task, all in a short time span. That said, there is a need for more research to develop safe and trustworthy agile robots that can operate effectively in close proximity with humans. In the future, we will look to confirm these findings in other agile settings like tennis to see if people prefer working with robots that implicitly communicate their intent.
Thanks for listening.